Assalamu alaikum. Welcome again. Here we have a reaction which is A goes to R plus S. Like when we assume elementary reaction, we should observe something like this, right? KCA. And if it's non-elementary reaction, but with like can be represented as a single order. What I mean by single order, that it does not change. The order of the reaction does not change by conditions. It's always second order kinetics or first order or 0.5. But sometimes, and as it's stated in this question, there might be some regimes in the reaction rate. And we actually discussed that in previous example, I think third video or fourth video. We said there might be a reaction which take place. You see that it is second order, but you have in denominator 1 plus K2CA. So we should compare one with the other term. If it's too much, we can neglect one, and this term goes with the second order. That means at such a condition, we have first order reaction rate, but when this term 1 is too much bigger than the other term, you can neglect this, and you will have second order reaction. That is what exactly we discussed previously. And in this equation, you see a signal of the same idea, because it says the decomposition of reactant A follows a first order rate law, but in a specific condition, when you have pressures between 1 and 10 atm. That means there might be some other rates. Okay? So actually, I assume that I will get something like this. But how reaction does not take place something like this, and we have like two reaction rates, not a single K1. We have different coefficients. Because there might be some intermediate steps. And we will show this in, let's say we rewrite these again. It will be like 2A goes to A star. And this A star actually, from the beginning, we can directly say that there is not a thing such as A star in our reaction, because it's not measurable. We don't measure that species. So that means it is being generated and consumed by the same reaction rate. There might be a generation which affects our kinetics, but when it comes to measurement, we don't realize any, we cannot detect any species of A star. So that will help us, this information that we don't have any rate of reaction of A star, will help us to find the reaction rate in this format. So let's start putting that this is the K1, the first reaction. And you have second reaction when you have, this is a reversible reaction, so you will have in the counter direction. So it is K2, okay, in the opposite direction. And you have other reaction, this third step, when you have A star goes to R plus S, okay? So we start by putting reaction rate of A. We say, when you put here minus, you start by like A is in the left side and you are consuming A, okay? When you consume A, just put here minus, but here positive coefficient, okay? Here minus, here positive, that means you are consuming A, okay? I'm consuming K1 CA squared. I assume elementary. That means the coefficient of stoichiometry will give me the concentration dependence, okay? When I see here 2, I put here 2. And this is for K1. What about K2? Now I consume A, right? In this case, the reaction, like reactants are here. So these concentration will affect K2 direction. So that means I should here put minus. Okay, it's the reverse case. So I put K2 and concentration of Ca star and multiplied by Ca, because they have 1, 1, first order. Why? Because we have here coefficient as 1 and 1. We assume that we see if it's compatible with our measurements and observation or not. We just assume, because it is not a proof. We just try to derive that this is second order, so here and here it will be it will depend on the like it will be like elementary, so it's the number of moles, you can put it here as a power, then start calculating, and at the end you will compare it with your your observation, if it follows a first order rate or not. Let's see if that happens or not. So this is the first thing. Second thing, let's put A star. And at the beginning, we will start by K3 because it's easy to here. We put minus, and as you remember, when I generate that, I put minus, and for generation, I should put positive. So here I mean consumption. When I consume A, it's reactant. It should be reactant. So arrow starts from that point to the product's direction. So that in that case, you put here negative. That means you will reduce your number of moles in A, okay? And here K3 and Ca, what is my coefficient? 1. So Ca star power 1, but no need for putting 1. This is the for this part. But what about K1 and K2? In K1, do I consume A star? No. In K1, I generate A star, and I produce A star. So I should here put negative in order to make this negative cancel the other minus sign, so I have positive value because I am generating A star, which must be positive at the end. So now minus by minus will give me positive. So it is K2, K1 in this way. So it is Ca squared. Then you have plus K2, because in K2 you are consuming A star, so you can put positive, okay? Positive times negative will give you negative. That means you are reducing your number of moles in terms of A star, right? Because you are consuming it. So plus times negative must give you negative because you are consuming. K2 times Ca star Ca. So here, since we know that must be equal to 0, by using that information, I can eliminate Ca star because there is nothing like the Ca star. I should eliminate this, and instead of Ca star here, I should put something like expression of other terms that I know, not Ca star. I don't know Ca star. We don't have reaction rate of a species, right? A star species. So I should eliminate this term and plug that value, that expression here. So how do we eliminate it? First thing, we can take this, the term that does not include A star to other terms. So it will be K1 Ca squared. And in the opposite side, you will have Ca star. As a common coefficient, you have K3 times Ca star and plus K2 times Ca times Ca star. So here plus K2 Ca, okay? And when you divide both sides by K3 plus K2 Ca, you eliminate that term and you found Ca star. That means you can now plug that value in here. So minus Ra will be equal to K1 Ca squared minus K2 Ca, here you have Ca, then Ca star, which is this expression. Here we are getting closer to what we discussed previously. We are getting closer to have something in denominator, something in numerator, right? A fractional expression. So, but we still need some further simplifications. So let's see how we can do that. Here I have K1 Ca squared, K1 Ca squared. Let's take as a common coefficient. Here you have 1 times. And here you have negative K2 Ca over this expression times K1 Ca squared. So you can say minus K2 Ca over K3 plus K2 Ca, right? I hope that we are going in a right direction, but I think that's good. Let's continue simplifying this term. So we will have, inside of parentheses, we can expand this term by multiplying by this. So you will have, instead of 1 here, 1 multiplied by this, you can combine them into one numerator, and you have this in the denominator. Okay, so you see that K2Ca will cancel each other, and you will get more simple terms: K1, K3, Ca squared. Let's say this is reaction rate over K3 plus K2Ca. And we will have two regimes. Let's say first regime when K3 is too small than K2Ca. So what happens that this can be neglected. This term will be negligible. So you will get K1, K3 Ca squared over K2 Ca. And as you see, when we neglect K3, so we can cancel the Ca term in the denominator, and we will end up with first order reaction rate. And this is what we were searching for, right? So that means actually when K3 is too smaller than K2Ca, we are in the regime that was being described in the question. Pressures between 1 and 10 atm corresponds to this regime. When you can neglect K3, so your reaction rate turns to first order. And in the other regime, or in the, let's say, in the different pressure conditions, you will have second order reaction rate. So this is how you work with intermediate species and use them to derive the real kinetics of a problem. And thank you for watching.